Okay, finally, we have finished our inquiry. That took a while, but we can finally get down to business and find out and understand the three conditions in which a salt can be acidic or alkaline when dissolved in water. The first condition is that the anion has to be a conjugate base of a weak acid. So what do I mean by that? So suppose you have a question posted to you in which you have two salts, one of them is sodium ethanoate and one of them is sodium chloride. And the question posted to you is which salt will be having a pH of not 7 when dissolved in water. So how do you go about solving it first? Okay, as we can see, our both salt have the same cation of Na+, so definitely we shouldn't really care about the cation for now. Let's focus on the anions. The anion for on the left is our dear ethanoic, which is a conjugate base of our ethanoic acid. Well, for on our right, our chloride anion is a conjugate base of our hydrochloric acid. So, as we know, ethanoic acid is a weak acid and hydrochloric acid is a strong acid. So remember the relationship that we have learned just now. When there's a strong acid, it means that its conjugate base has to be weak. And if you have a weak acid, it means that your conjugate base has to be strong. So putting this into practice, we can deduce that our ethanoate is a strong conjugate base. Pardon the sound behind, and I'm not going to re-record this, but so our chloride anion will be a weak conjugate base since our hydrochloric acid is a strong acid. So what does it mean when we dissolve them into water? Let's see the animations. Okay, so when dissolved in water, let's focus on the left first. Since our ethanoate is a strong conjugate base, or as a strong base itself, it is able to deprotonate water, and as a result, we get a bit of ethanoic acid as well as a low concentration of OH minus ions. Now focusing on the right hand side, we have our chloride anion, and it's a weak conjugate base. So as a weak base, it is unable to perform the same deprotonation of H2O as what we have witnessed just now of ethanoate. As a result, we on the left hand side, salt hydrolysis can actually occur, and the equilibrium that we see above is basically a written form of what just happened just now in the animations, in which the conjugate base or the strong conjugate base is able to react with water to give you some weak acid as well as some OH minus ions. Well, on the right hand side, salt hydrolysis couldn't occur for a weak conjugate base, which means the Cl minus anion is unable to react with water to form OH minus ions. Therefore, now as we take a step back and witness what has happened, we realize that in the beaker, there's actually on the left hand side, there's actually some concentration of OH minus ions. Well, for on the right hand side, there is no OH minus ions nor H plus ions, it's just water. Therefore, we can deduce that our sodium ethanoate, has resulted in the alkaline solution when dissolved with water, and for our sodium chloride, it will be neutral because there is no excess OH minus ions or H plus ions. Alright, so now moving on to the next condition. In this condition, the cation is the main character here, whereby the cation has to be a conjugate acid of a weak base. Suppose, now there's another question that is proposed to you, whether ammonium chloride salt would be neutral, acidic, or alkaline when dissolved in water. So how do we go about solving this question? Well, despite saying that the cation is the main character now, let's just get the anion over and done with first, because the anion here is our very dear chloride ion once again, and we know that our chloride ion is a conjugate base of hydrochloric acid, which once again is a strong acid. So now hopefully by now you are familiar with the idea of strong acid, weak conjugate base, weak acid, strong conjugate base relationship. So as we determined and deduced previously, our chloride ion would be a weak conjugate base, and being a weak conjugate base, it will not be able to hydrolyze or react with water to produce OH minus ions, and therefore in this case, since there no OH ions produced, and that's why our anion is not really important in this case. And now let's focus on our cation, whereby our cation is now ammonium ion. And then using the same formula as we learned previously, our ammonium ion was or is a conjugate acid of our ammonia base, where our ammonia is a pretty weak base in our syllabus. And once again, using the relationship, this means that our ammonium has to be a strong conjugate acid. So now let's witness the animations and see how or what does a strong conjugate acid will do in water. Okay, upon dissolving in water, ammonium ion, being a strong conjugate acid, once again, a strong acid or strong bronzite acid means that it will donate its proton to a base, which is water in this case. And okay, although the animation is not as like whoa or whatsoever, and in that case, in the animation, an ammonia ion has donated a proton to a water to form H3O plus ions, and this is represented in the equilibrium reaction above. So NH4 plus H2O gives you a ammonia and H3O plus ions, and is a reversible reaction. So once again, what is produced from this um, dissolving of this salt? There is H3O plus form, H3O plus form in the beaker as well, and overall, since there's an excess of H plus ions compared to OH minus ions, this makes ammonium chloride solution acidic in water. Lastly, we will have our third condition, in which the metal cation has to have a high charge density. Okay, this third condition will be slightly different than the first two conditions, because the first two conditions is really pretty much straightforward, and not really straightforward actually, but it's pretty much related to each other with respect to the idea of a strong acid, weak conjugate base, weak acid, strong conjugate base, blah blah blah, all this relationship that we have should be familiar by now. By this case, this topic has to do with a bit of periodicity knowledge. So this, you can see this as a teaser or like a sneak peek of what's to come for periodicity. So once again, if a question is posed to you whether this salt right here, aluminum nitrate, would be acidic, neutral, or alkaline when dissolved in water, we still can use the same formula as what we did for the first two conditions. Let's take a look at anion first. So, and the anion here is a nitrate anion, and it is a conjugate base of our HNO3 acid, which is of course a strong acid as well in our syllabus. So basically, actually, our strong acids have, it's generally three of them. One of them is your nitric acid, one of them is your hydrochloric, and also your sulfuric acid. So these big three are the most common strong acids that we learn in our syllabus. But okay, coming back to this, since is a conjugate base of a strong acid, it means that our nitrate anions will be weak conjugate bases. And as you know, weak conjugate bases or weak bases will not hydrolyze or react with water to give any OH minus ions. So no OH minus ions form as well. So that's why let's shift our focus to the cation. In this case, our cation is Al3+. And Al3+, what's the formula for? And Al3+ is a cation with high charge density. So to recap, what is the formula for high charge density? Or what's the formula for high charge density? It's basically your charge over ionic radius. Yeah, so this is a little bit of your atomic structure knowledge. So now let's see what happens when this salt is dissolved in water. Yep, so when dissolved in water, your nitrate anion, since it's a weak conjugate base, will not react with anything in the water, and hence it will just act as a spectator ion and just be chilling in the beaker. Well, something more interesting will be going on for your Al3+ cation. For those who are seeing this for the first time, your Al3+ cation is capable of forming a complex ion formation with 6 water molecules to give you this complex ion. It's okay if you guys are unfamiliar with these terms, or yeah, because you will learn more when it comes to the topic of periodicity as well as transition metals. But now you can take it as, since the Al3+ cation is highly positively charged, it is able to attract the partially negatively charged oxygen atoms in the water molecules, in the 6 water molecules, towards itself. And that's why the oxygen atoms are kind of, tilting towards, or the water molecules are tilting towards the Al3+ cation with the oxygen atoms facing them. So what are the implications when such a high charge density cation forms a complex formation with the water molecules? As you can see, the circle or the radius with a darker shade of yellow represents the region with higher electron density. As Al3+ has high charge density, it's able to attract the electrons or electron density from the around the oxygen around the water molecules towards itself, and that's why the inner radius is much darker shaded to signify the higher electron density, while the larger radius with lighter shade of yellow represents the region of lower electron density. This is there's a term to represent what's going on here. It's called polarization. So what does it mean? To put things into perspective, suppose we have this OH bond which is found in water molecules. We know that the oxygen in water molecules, the oxygen really have a delta minus charge, and the hydrogen has a delta plus charge, and there's a dipole moment formed already. But now, due to the additional factor of a Al3+ cation, which is able to polarize or distort the bond even further, so you can think it of the dipole moment becoming even larger, or the electrons inside the covalent bond being pushed to, like, pull or push towards the oxygen atom even further. And what are the consequences for this? This actually weakens the OH bond quite significantly. And as you can see from the animations, once the OH bond is weaker, another water molecule is actually able to deprotonate or steal away the hydrogen atom from in the water molecule that belongs to the complex ion formation. And if we see as a result what can happen, boom, your H3O plus could be formed from the water molecule who deprotonated the hydrogen atom or the proton from the water molecule that belongs in the complex ion. And this leaves the water molecule to become a OH minus, And this can be represented with this equilibrium reaction. This may look a bit confusing, but that's okay. Most importantly, we know that H plus ions are formed in the process, and therefore with a metal cation with a high charge density in the salt when dissolved in water, this makes the solution acidic.